Right? Oh my god, I can't talk. All right, this is part two of the May June 2020 paper 1-1, and let's just get started. All right, so we'll be doing questions, I think 12 through, like, let's see, 12 through, say 21. 12 through 21 in this episode. All right, well, let's start. Okay, so last time we left off with this. A white powder is a mixture of sodium chloride and sodium iodide. Okay, so that's NaCl and NaI. Okay. It is dissolved in water in a test tube, okay, and then an aqueous solution of, oh, an excess, okay, that's important, an excess of aqueous silver nitrate, which is AgNO3, is added to the test tube. A precipitate X is observed. Okay, so immediately we know that since there's an excess of silver nitrate, all of the silver will react with the chlorine and the iodine in the sodium chloride and sodium iodide. So you're going to get a bunch of AgCl precipitate, which is white, and AgI precipitate, which is yellow. It's like a really, really pale yellow. Okay, and then let's see, moving on. There's an excess of concentrated ammonia. Oh, okay. Is then added to the test tube containing X. After the test tube has been shaken, a precipitate Y is observed. Okay, so if you guys don't know, if you add ammonia to a solution of a silver precipitate, right? So let's say, okay, we don't have AgBr here, but let me just put that in here as an example. So AgCl, AgBr, and AgI. So what adding ammonia does, if you were to use dilute instead of the excess that we're giving here, right? If we were to use dilute ammonia, it would turn silver chloride into a colorless solution, and it would literally just be clear. Like, well, I don't want to say clear. Colorless because it's literally like glass. That's what it would look like. Just water. But really it's not. But, just a colorless compound. AgBr, on the other hand, if you were to use dilute ammonia, it would turn a really, really pale yellow. And the reason for this is because if you were to use dilute ammonia, not all of it will be able to react with the AgBr. If you were to use concentrated ammonia instead, it would turn colorless just like AgCl does with dilute ammonia. Meanwhile, AgI, no matter what you do to it, it will always remain yellow. The ammonia will not react with the silver, so we know that. So in this case, though, we're using an excess, especially an excess, by the way. You need to know that. An excess of concentrated ammonia. What this will do is it'll turn the silver chloride colorless, and it will leave the AgI as so, because what ends up happening is the silver iodine will not react with ammonia, so you'll just be left with that yellow precipitate. Meanwhile, the AgCl will react with that ammonia and it'll turn colorless. So, when they ask you about which statement about X or Y is correct, let's see, X is a pure white color. It's not going to be pure white because you're going to have two separate layers of AgCl and AgI, so you're going to have a white layer and a yellow layer, so it can't be A. Meanwhile, for part B, let's see. X is pure silver iodide. Again, we said that there's going to be some silver chloride and silver iodide, so that can't be right. Y is pure silver chloride. Well, that can't make sense because if you were to have, like they say, a precipitate Y, right? That precipitate's going to be silver iodide because the AgCl will have dissolved. So it can't be C. Y is yellow. Since only AgI is left over, and we already know that AgI is a yellow precipitate, that is our correct answer. All right, let's move on. Question 13. 6.90 grams of an ammonium salt is heated with an excess of aqueous sodium hydroxide. Okay, well, if you were to look at the equation for this, I'm pretty sure if you were to just look at that, okay, ammonium salt, let's put that as X because we don't know what compound it is. NH4X reacting with sodium hydroxide, NaOH, will give us the ammonia, it'll be a salt with sodium and then NH3 plus H2O, just like that. Oh, got cut off, but you guys know what that is. Okay, so the volume of ammonia produced, okay, that's this ammonia right here, measured under room conditions is 2.51 deciliters cubed. Okay, so during room conditions, you guys should know this, at RTP, which is room temperature and pressure, our volume of gas is equal to 24.0 decimeters cubed per mole. And this is incredibly important to know because this will be used often. So if we were to just plug in some values here, let's see, we have 24, and they said you get 2.51 decimeters cubed of gas. Okay, so what you'd want to do is 2.51 decimeters cubed times, let's see, 1 mole divided by 24.0 decimeters cubed. And this will yield, let's see, plugging that into a calculator, 2.51 divided by 24, you get around 0.105 moles of gas. Okay, and we already know that, okay, so which ammonium salt is used? We know that these are the given molar masses. So what you want to do is, since the molar mass, the units are grams per mole, all you have to do is divide this number by the molar mass. So, also, you have to be careful though, because remember, ammonium carbonate isn't just NH4CO3, it's NH4 2CO3, because carbonate has a 2 minus charge. Same case for ammonium sulfate here, NH4 2CO3. So we're going to leave these two options alone for now, and let's just look at these two, which is NH4Cl, ammonium chloride, and ammonium nitrate, which is NH4NO3. All right, so if we were to do that, let's take a look at this value. If we were to divide that 0.105 divided by 53.5, you would get, let's see, 0.105 divided by 53.5. Oh, no, never mind. You'd have to do the opposite. Never mind, you just multiply it. Sorry, my bad. You'd want to multiply them because, again, unit conversions. It's grams per mole multiplied by moles, which will leave you with grams. So you'd multiply this by the 53.5, which would be, let's see, 0.105 times 53.5. That gives you 5.62 grams about. Okay, so 5.62 grams, so it can't be B. All right, let's move on to the next option then, which is option C. Okay, so that would just be 0.105 times 80. That'll be what? 0.105 times 80. That is 8.4 grams exactly. And that would not be it either. Okay, so it can't be B or C. We know that. Now we have to kind of backtrack a bit because we have to get rid of basically all of this part here because we need to go back to our original equation right here. So if we were to use a different compound, right, NH4 2X, we'd have to balance our equation, I believe. Let's see. Well, you'll have 2 ammonias, so we know that. You'll probably also be left with, okay, you'll have to have 2 NAs, since that X has a -2 charge and Na has a plus charge. And then that would mean that's 2 and that is 2. So yeah, that would be your new equation, and then you just have to multiply that in. So it would no longer be just this value right here. You'd have to divide that 0.105 moles by 2 again. And the reason for this is because now you're forming 2 moles of NH3 per 1 mole of this original ammonium salt. So if you were to divide that, 0.105 divided by 2, you get 0.0525. And then you just go back to the answer choices and plug them in. So starting with A, we multiply this by 96, we get, let's see, multiply that by 96, you get 5.04 grams, which is not right. So 5.04 grams, 5.04, so that is not correct. If we were to plug in the other value, however, 132.1, it should be, let's see, plugging that into a calculator, 0.0525 times 132.1 gives you 6.94 grams. And while that might not be exactly 6.90, we did round quite a bit in here, and it is the closest to 6.90 grams, therefore that is the correct answer. So when you're doing this problem, be very careful on this balancing part. You have to make sure you have to do the NH4 and balance it accordingly, as we show right here, whenever you're using this compound. So again, watch out for the stoichiometry. Besides that though, it should be pretty fine. So this answer choice should be D as well. All right, moving on. An excess of MgO is shaken with water. Actually, wait, before we go, let me just change this color to something else. I kind of feel like doing blue this time. Okay, an excess of MgO is shaken with water. Okay, magnesium oxide. The resulting mixture is filled into test tube P in excess of BaO, okay, wait, we should probably highlight excess as well. An excess of BaO is shaken with water. The resulting mixture is filtered into test tube Q. Okay, so which reacts more readily with and which filter has the lower pH? Okay, so this is probably a group 2 metals question. And the first things you need to know is whenever you're using a group 2 metal oxide and reacting it with water, the equation always follows the format of MO plus H2O is an equilibrium reaction, forms M, which is a group 2 metal, OH2, because the group 2 metals have a +2 charge and hydroxide has a -1 charge. So in this case, what we want is, let's see, magnesium oxide plus H2O forms an equilibrium reaction with magnesium and forming magnesium hydroxide, like that. And then barium oxide will do the same thing with H2O and yield barium hydroxide. So, if you guys don't know this, barium hydroxide is an incredibly strong base, and that's just something you need to know, by the way. One of the strong bases is barium hydroxide, and that means that the more basic you are, the higher the pH. Therefore, test tube P will have the lower pH because test tube Q is more basic, since that's the one that contains barium hydroxide. And the reason for this is because the solubility of the group 2 hydroxides, increases as you go down the group. So as you go down the group, your solubility increases. And what that means is this right here will ionize more, because this barium oxide right here will react with the water and form the barium hydroxide, and barium hydroxide will split into barium ions and hydroxide ions. And the more hydroxide ions you have, the more basic the solution becomes. Therefore, that's the one that has the higher pH. That's a really easy way to memorize it, by the way. Just say that since solubility goes up as you go down the group for hydroxides with group 2 metals, magnesium hydroxide is less likely to, well, there will be less magnesium hydroxide in the test tube. Therefore, you'll have a lower pH. So test tube Q is eliminated, so you can get rid of answer choices B and D. Moving on to answer choices A and C, we have to look at which one reacts more readily with water. So barium oxide or magnesium oxide. The reactivity of the group 2 metals, especially when it comes to the oxides. So here, let me use violet for this one. The reactivity of the group 2 metals, well, actually, no, let's phrase that better. The group 2 oxides. Whenever you have the group 2 oxides, their reactivity with water, so with H2O, increases as you go down the group. And this makes sense because if you think about it, if the solubility of the hydroxides increases down the group, then it also makes sense that as you go down the group, they're going to be more reactive with water. That way, they form more of that group 2 metal hydroxide. So, in this case, that means barium reacts more readily. And in that case, we can eliminate the magnesium oxide. So answer choice C is gone, and your answer is A. All right. And now that we are done with that, let's move on to the next set of questions. So yeah, element Z has a giant structure. Okay, so giant structure means you basically just don't have a simple molecular structure. So metals can have a giant structure, covalent structures can be giant, and so on. Okay, so we know that it has a giant structure. The chloride of Z reacts with water to give a solution with a pH less than 5. Okay, so it's relatively acidic since neutral is 7. And which pair shows 2 elements, which could be Z? All right, well, let's just move down the list and start with this piece of information right here. That is a giant structure. Okay, so aluminum forms a metallic structure, so it would probably be fine. Magnesium is also a metal, so that's fine as well. Silicon forms a lattice structure with silicon dioxide. Actually, it's giant covalent, and we know this compound to be glass or quartz, and it has a giant covalent structure. So that one's fine as well, so that's fine. So far no answers eliminated. Phosphorus, on the other hand, phosphorus forms a simple molecular compound. So if you look at P, the structure will just be held by the molecules themselves, just van der Waals forces between them. So P forms simple molecular. Whoa, my God, what is that? P forms simple molecular. Simple molecular. So phosphorus cannot be a giant structure. So we can eliminate phosphorus here, and I see a phosphorus in answer choice D. So both of these will not be correct, even though they do have the magnesium and silicon. So we're left between answer choices A and B. All right. Now we move on to the next piece of information here. The chloride of Z reacts and forms a, okay, software later, not right now, a pH less than 5. So what you want to know is the reactions that these molecules have with each other. So when you look at magnesium chloride, actually, you know what? Let's just start with aluminum since it's first. When you look at aluminum metal, right? Aluminum will form AlCl3 because aluminum has a +3 charge and chlorine has a -1 charge. So when you're looking at that, AlCl3 will react with water, right? Because that's what it's saying right here, reacts with water. Goes to, let's see, it'll probably make a hydroxide, so AlOH3, since, hydroxide is also -1, and it'll form a acid, so in this case, it'll probably be HCl, and it'll probably also make chlorine gas as well, Cl2. Actually, no, never mind, no, what did you do that? Oh, no, never mind, I did that wrong. No, it will not make chlorine gas because we need to balance this. This will be, oh my God, no, sorry about that. It'll be 3 HCl and, what is that? 3 H2O. And why this is the case is because one of these hydrogens will pop out of the water, forming the hydroxide, and it'll also react with the chlorine to make hydrochloric acid. So in this case, you get HCl and you get aluminum hydroxide. So aluminum hydroxide is insoluble in water, so this won't split up into ions. It won't disassociate, and you're just gonna have a bunch of HCl. And HCl is one of the two strongest acids, right behind sulfuric acid, in terms of our general chemistry acids. So this solution will have a pH most definitely less than 5. In fact, it'll probably have a pH around 2, maybe even less. So aluminum is fine. So we already know that aluminum is great. Now we have to test silicon and magnesium. So let's just start with magnesium since it's the above answer. If we look at magnesium will form MgCl2 because magnesium as a group 2 metal has a +2 charge. It will also react with water and form magnesium hydroxide. We already know that. And it'll also form HCl. And if we take a look at this, it'll probably do the same reaction. So you have 2 H2Os and 2 HCl's. By the way, the reason why I set these coefficients right here are because I'm looking at these bottom numbers. But yeah, looking at that, balancing it out, it looks like this will be the case. But you have to be very careful because while we do get HCl, magnesium hydroxide is most definitely soluble in water. So this will actually cause the solution to be pretty much neutral because you're going to have hydroxide ions. You'll have 2 hydroxide ions for every H plus ion that you have here. And that means that these two will probably cancel out the acidity and cause the solution to have a pH that is not less than 5 and more likely around 7. So it can't be magnesium. So if you wanted to just eliminate answers, you could go with B right away. But let me just show you what the silicon solution would look like. So silicon would form an SiCl4 because actually, you know what? Let me pull up my data booklet right quick. Here, where is it? I need to figure out where my notebook is. Where is my notebook? Sorry about this. Where? Let's go back to documents. Okay, in mine and right here. Okay, here we are. Oh my goodness. Let's just quickly erase all this stuff from last episode. Alright, if we look at silicon is right here, right below carbon, and we know that carbon has a +4 charge. So it will create this SiCl4 because Si will be +4, Cl is minus, so you'd have to have 4 chlorines. So knowing that, SiCl4 plus water, H2O, will give you silicon dioxide, because silicon dioxide is the compound that forms when you're reacting with water, and then you'd also get HCl, just like the others. But in this case, it'd be a bit stranger because, let's see, first of all, since there's two oxygens here balancing it, you'd need to have two of those. And since there's no H's on silicon dioxide, what you're going to end up getting is those hydrogens will all react with these chlorine, so you get 4HCl. And I'm sure you guys probably know this, but silicon dioxide, since it is glass, it does not dissolve in water, and you just be left with a crap ton of HCl. So it'll actually be more acidic than this one right here. So we know for a fact that silicon works as well. So the answer choice for this question would be answer choice B. All right, moving on. Switch colors again. How about we use orange this time? Sodium, aluminum, and silicon, okay, are three elements in period 3, all right? And each element forms an oxide, and which row has 3 correct properties of these oxides? Okay, so the best way you'd probably approach this problem is going in order. And also, by the way, if you don't know how to approach this problem, I am sorry to say, but this is a pure memorization question. So if you're not familiar with these, there's really no other way to do it except to basically either one, experiment with them and then get results by testing pHs, or two, just reading about them and then taking notes and memorizing them. So sorry if you aren't familiar with them, but drawing out the structures. Sodium oxide is Na2O because oxygen has a -2 charge and Na is a +1. Aluminum oxide is Al2O3. If you don't know that right off the top of your head, maybe you know it from organic chemistry. If not, just know that aluminum is +3 charge, oxygen is -2, and balance it out. Silicon dioxide we know is glass, our good friend. And moving on, let's see. Silicon dioxide is a giant covalent molecule. Aluminum oxide is ionic, and sodium oxide is also ionic. And you know that because aluminum is a metal, and oxygen makes -2 charges. Sodium is a metal as well, +1 charges. They will dissociate in solution. And silicon dioxide is glass, and we know that that is a covalent structure, so it will not split up. Moving on. Well, first of all, since we know it's ionic, we know that if you're in water, right, it's going to become disassociated. And Na, since it's Na plus and water, it'll actually react with water right here. So actually, let's start with this. It'll react with water in this. So it'll make Na2O plus H2O will create 2NaOH. So this is actually a way to make sodium hydroxide using sodium oxide and then putting it with 1 mole of water as well, and then you get 2 moles of sodium hydroxide. So if you know this reaction, you know that sodium hydroxide is also very basic. It's one of our strongest bases. So it is most definitely basic. It is most definitely giant ionic because, again, ionic structure, sodium oxide. Because it is ionic, it also has a high melting point and it reacts with water, as I just showed you with that equation. So we can't really eliminate anything using this. Then moving on, let's start with aluminum oxide, since it's next. Aluminum oxide is actually not basic. It's actually amphoteric, which is this word right here. And amphoteric means that it can serve as both an acid or a base, depending on the situation that is needed. And if you guys don't know that, again, it's just pure memorization. You might know it from organic chemistry. But yeah, just know that aluminum oxide is amphoteric in case it ever comes up again. It is, again, it's ionic, so we know it's giant ionic. Ionic structures do not have a low melting point. In fact, we've already established they have a high melting point, so that can't be right. And we also know that, let's see, no reaction with water. That is actually true, because aluminum oxide is actually insoluble in water. So despite it being ionic, it'll dissociate in a different solution, but it won't react with water. So yeah, we already know that we ruled out A and C, so because there's X's here. So moving on, I'll still go through every option though for silicon dioxide, just in case you don't know them. So silicon dioxide, it is not amphoteric. Silicon dioxide is actually acidic. So actually here, wait, amphoteric, let me write that there. Amphoteric and acidic. So we know that that's wrong, but we already ruled out A, so that doesn't really matter. It is not simple molecular because we said already that it is giant covalent. If it was simple molecular, it would not form a lattice structure. but silicon dioxide does form a lattice structure, as you guys know from the crystals that you can see in quartz and glass. Because it is a giant covalent structure, it does have a high melting point, so we know that. And it does react. It does not react with water, as we already established from the previous question, right here. It just stays there. It's insoluble. So yeah, we already eliminated answer choice A and C, but thanks to our answer choice B option there, we can eliminate that one, and we know our final answer choice is D. So yeah, hopefully you guys now learned a bit more if you guys didn't know that. I'm sorry to say that it's just brute force memorization. But yeah, it's kind of painful. I'm sorry. All right, moving on. Question 17. Okay, 0.25 grams of an anhydrous magnesium nitrate is heated strongly, okay, until it completely decomposes. All right, so we're going thermal decomposition here. What is the total volume of gas produced measured under room conditions? Okay, so we already know that the volume of gas taken up is 24 deciliters cubed per mole. We established that. I guess we just start with the reaction then. So magnesium nitrate, be very careful because it's a group 2 metal. It has a +2 charge, so it would be MgNO3 too. And it would react to form, well, you're undergoing thermal decomposition first of all, which means just heating it and splitting it up. You'd get a oxide of that metal, so magnesium oxide. You get 2 NO2 gas. Okay, well, here, if you really wanted to include state symbols, and then you'd also get 1/2 moles of O2 gas, oxygen gas. So you get these as your products. So basically what this is stoichiometry. You're reacting 1 mole of that, and you're getting basically 2.5 moles of gas. And since gaseous compounds in standard conditions and ideal conditions, really, they all occupy the same volume of 24 decimeters cubed per mole. All you have to do is calculate the molar mass of magnesium nitrate, and then basically just divide that in, get your moles, multiply it, and then go. So let me just show you that, I guess. The molar mass of MgNO3 is, let's see, going to our data booklet here. All right, let's get rid of that. Magnesium is 24.3, so you'd have 24.3 plus, I'm going to put, here, let me just show you my calculation. I did 24.3 plus 2 times, I put it in parentheses because what you want to do now is find the molar mass of NO3, so 14 plus 3 times 16, because that would be your NO3, and now you have your MgNO3 too, like that. So it basically simplifies your calculations. And doing that, you get that your overall molar mass is, oh wait, I forgot to multiply by 2. Stupid me, is 148.3. All right, 148.3, let me just erase our stuff so that next time we come back, we don't see a bunch of random calculations. 148.3. All right, so moving back here, we know that is 148.3 grams per mole. So we said that there's 0.25 grams of this, so you divide the 0.25 by the 148.3, and you get 0.00169 moles. Okay, oh my god, my dad is watching soccer. Yeah. Anyways, so you get 0.00169 moles. You'd have to multiply that now by the total moles of gas, which is 2 plus 0.5, so 2.5, and multiplying that out, you get, let's see, I'm actually just going to use the, here, 169 times 2.5, you get 0.004225 moles. And what you want to do now is multiply that by 24 decimeters cubed per mole, and your answer should be times 24, let's see. So that times 24, I can't type, 0.1014 deciliters cubed. And we already know that that is just equal to 101.4 centimeters cubed, because whenever you're converting from a unit like centimeters cubed, decimeters cubed, you'd be multiplying it by 10 to the third power. So 101.4 centimeters cubed, that is answer choice C. And that's how you would solve that one. Hopefully that made sense. Those are just simple questions. Just know the stoichiometry and then go on from there. So as you guys can see, by the way, overall in paper one, a really key topic you guys should really know is group 2 metals and group 7 halogens as well. Well, group 17. Yeah. So as you can see also in the next question, we're getting yet another group 2 question. So astatine is below iodine in group 17. Okay. So, okay, fine. This is a halogen question. Okay, so it's below iodine, so it'll probably share the same properties as iodine, just maybe a bit wonkier. Okay, which statement is most likely correct? Okay, AgAt solid. Okay, so that would be our silver astatide. Silver astatide would be, let's see, below silver iodide. And it will react with an excess of dilute aqueous ammonia to form a solution of a soluble complex? No, it will not. Because remember how I told you how when you're looking at AgCl, AgBr, and AgI, remember how I said this would be soluble if you were to use any form of aqueous ammonia? This would partially dissolve into a colorless solution, a partially colorless solution. It would be like slightly yellow with AgBr and dilute aqueous ammonia, and then this just won't. It'll always stay solid. Well, AgAt is below AgI. So this will stay solid no matter what amount of ammonia you put in it. So AgBr will, okay, so this one right here will dissolve no matter what kind of ammonia you use. This one you need concentrated for it to completely dissolve into a colorless solution. And these two right here will never. So it will not be soluble. It would rather be insoluble. So, okay, we got that out of the way. Next part. Let's use green again. Astatine and KCl react to form KAT and chlorine. Okay, so this is basically asking about the halogens property of substituting. So this actually won't happen because basically what happens is, let's see, looking at them, FCl, Br, I, and in this case AT. What happens is whenever you have a salt, so KF, KCl, KBr, Ki, and KAT, let's say, whenever there's a molecule below, if you were to put in a element that's above it, it will actually substitute. So in this case, KCl won't be substituted by KAT because AT, oh my god, because AT is below Cl in terms of the group 2s. And you can see that by looking at the table here, they are going like that. So as you go down the group, they are more easily substituted. So rather than chlorine being substituted, in the case, what would actually happen is if you were to start with these two, KAT and chlorine, the chlorine would actually substitute the KAT and become KCl. But in this case, that's not what the question's asking for. They're saying, will astatine substitute the chlorine? And it will not, because astatine is below chlorine. Okay, so we got another answer choice going. Answer choice C says KAT and dilute sulfuric acid react to form HAT. Okay, well, again, this is kind of memorization, but astatine will not, well, any form of halogen salt will not react with dilute sulfuric acid to form the gas like that. Instead, it has to be concentrated, which is the next one right there. So answer C is not right, but answer D is correct, and let me show you why. All the halogens will actually react with concentrated sulfuric acid with the following reaction. So it'll initially form, let's see, any form of salt, so potassium, sodium, you can do anything. Potassium times the potassium halogen, so in this case it'll be AT, reacts with sulfuric acid. It has to be concentrated. Oh my god, H2SO4. Sorry, I can't write. H2SO4 forms a bisulfate salt. So KHSO4, and we call it bi because there's the hydrogen in there. KHSO4 plus HAT. And you might say, okay, nice, but we're finding astatine here. So how would that work? Well, actually, this HAT right here will react with another reaction. So HAT, we actually need 2 moles of it, plus H2SO4 will react to form elemental astatine, and since it's a halogen, it actually forms a diatomic gas, plus sulfur dioxide, SO2, and 2 moles of water, like that. So all of the halogens will actually react following this. So you can actually substitute acetylene with anything, and they will always follow this reaction pathway right here. So we already know that we're given the sodium acetylene, and we were given concentrated sulfuric acid, and we do indeed form elemental acetylene, so that is correct. And you can do this with anything, like I said. And if you didn't know that, hopefully you do now. Again, kind of bit of a memorization kind of topic, so it's not ideal, but hopefully it makes sense. All right, moving on. Let's look at question number 19. Oh, we're talking about melting points, huh? Okay. Was the order of increasing melting point? Okay, I'd suggest boxing increasing so that you don't forget that. All right, well, first things first, let's take a look at these. Okay, so CCl4 is a simple molecular compound. So here, simple molecular. And the reason for this is because, well, first of all, it's a carbon. Carbon is basically a neutral kind of atom. It forms simple molecular compounds. So the only forces that will actually result in this one will be between like the molecules themselves with van der Waals forces. So again, you won't really find a very high melting point for this. In fact, I'm pretty sure carbon tetrachloride, I'm pretty sure it's actually a liquid. Well, maybe it's a gas, I don't know. But yeah. Point is, it has a pretty low melting point. MgCl2. Okay, this one, you guys should know immediately upon seeing that metal. Mg is a group 2 metal, and chlorine has a -1 charge, as you guys know. So this is actually going to form an ionic compound. And as we already know from the past questions, ionic compounds have a very, very high melting point. So I'm going to guess that this is probably high, especially since right here we see phosphorus. This is actually, contrary to popular opinion, this is actually not a simple molecular. And it's actually not a simple molecular compound or any kind of molecular compound at all. It's actually a very, very weak ionic compound, which is kind of cool, honestly, because phosphorus typically makes a simple molecular compound. But surprisingly, with PCl5, it actually makes a weak ionic compound due to the number of charges, and it actually has some forms of dipoles. But yeah, even if that was the case, by the way, even if you were to think of it as simple molecular, just like CCl4, there are more electrons in PCl5 than CCl4. So if there are more electrons, they both only share van der Waals forces in that case, right? If you were to consider it like that. Well, despite having more van der Waals forces, well, even despite them both having van der Waals forces, because PCl5 has more electrons, there's a higher charge density. Therefore, the van der Waals forces are stronger, so it'll actually have the higher melting point. And that's basically how van der Waals forces work, by the way. Also called London dispersion forces. You're basically taking a look at the number of electrons in a molecule and then comparing those. So the reason why larger compounds have such a strong van der Waals force, by the way, is because of their sheer size. Because of that sheer size, they have a crap ton of electrons, and because of those huge amounts of electrons, that is what results in the stronger van der Waals forces. So if you were to look at it, this is the most, and this is the least. And then, of course, PCl5 is in the middle. So highest melting point, lowest melting point, we already know that CCl4 is the lowest, so it can't be any of these. Kind of rules them all out. And then strongest is going to be MgCl2. And the only one that has all of them is this one right here, so answer choice A. Okay, moving on. Oh yeah, and I hope you guys knew that. Hopefully you guys learned something new about the van der Waals forces thing. That should hopefully come in handy. All right, number 20. The skeletal formula of compound X. Ooh, we're into organic chemistry now. Okay. Which row is correct? All right, molecular formula of X. Okay, that should be the easier question. And the observation upon addition of X to Fehling's reagent. Okay, so Fehling's reagent right here is a test for an aldehyde. So what it does is it turns an aldehyde, which is basically just if you have a carbonyl, so it'll be something like this, and you have the R group, which is the other chain. So it turns an aldehyde, let me spell that, aldehyde, yeah, to a carboxylic acid, and basically what it'll do is it'll turn this into an OH, which is what a carboxylic acid is. And it also turns a blue solution, which is what Fehling solution is, and it'll turn it red because there's going to be a brick red precipitate. And it won't react with a ketone. So this test only works with aldehydes. And in our question right here, that thing right here is actually a ketone because this right here is a CH3. And because of that, failing solution will give no reaction. So in that case, we can eliminate the red precipitate because there's going to be no reaction, no change. So B and D are out. All right, now it comes to the fun part, which is just counting. This is pretty easy. Here's how I like to do it. When you start, circle all these endpoints. So 1, 2, 3, 4, 5, 6. Don't count the oxygen. 7. So there are 7 carbons in here. Okay, pretty straightforward. What I'd like to do next is I like to erase it. So pretty much always bring a pencil to the AICE exam. This is why it comes in handy. We already know that all the answer choices give you 1 oxygen anyways, and that's kind of pretty obvious. So I'll skip that part. Now for the hydrogens. When you're looking at the hydrogens, be very careful. So you might see like traces of your pencil with these circles like that. And what I'll do is for each of those pencil traces, I'll go here and I'll take a look at how many carbons there are. So that's a lone one, so that has 3. This one right here also has 3. This one has 1 because it has 1, 2, 3 bonds. So for carbon to have 4, it has to have another hydrogen. This one right here has 2. This one also has 2. This one has 0 because there's a double bond, and then 1, 1, so that's 4 bonds. And then this one right here also has 3. And then counting them all up, 3, 6. Well, actually, no, that's not how I count them. How I typically count them is like this: 3, 6, 7, 8, 9, 10, 11, 14. So there are 14 hydrogens. And just in case, I also like to double check, which is when I do this: 3, 6, 7, 9, 11, 14, just like that. So we know that these H16s are wrong. So again, we can double whammy that one, and that one's gone. So answer choice A is the correct answer. So yeah, make sure you know Failing's reagent. The other one, by the way, they didn't ask this, but Tollin's reagent. This is the other one. Actually, no, I don't think that's how it's spelled. It's Tollin's reagent. Tollin's reagent will create a silver mirror when reacting with an aldehyde, and it will form no reaction, aka it will just remain colorless if you react it with a ketone. So make sure you know those two. And also, just the counting method in general, pretty easy. And then the last question for this video will be question 21. Okay, this is one of those ones that you probably want to skip. I believe this is an elimination question. Okay, so 2,2-dimethylpropanoic acid is an isomer of propylmethanoate. Okay, well, I'm just going to kind of put option A for here now. Okay, let's start with drawing out propylmethanoate. So this is an ester. And whenever you're drawing an ester, first thing you want to do is, first of all, draw your double bond O and then an O right away. What you want to do now is take a look at that prop right in front of that YL right here. Look at that. Prop is for propane, and propane has 3 carbons. So 1, 2, 3, like that. Next, take a look at this one, methanoate. So whatever in front of that anoate. That meth right there is for methane, therefore there's only 1 carbon right there, so that'd be an H. All right, that is what propylmethanoate looks like. Meanwhile, 2,2-dimethylpropanoic acid. Okay, well, let's break that down. Propanoic acid. 1, 2, okay. It would look like that because there's 1, 2, 3 carbons like that. Okay, and then 2, 2, okay. This is carbon number 1, and this is carbon number 2, so 2,2-dimethylpropanoic acid. That's what that looks like. Is an isomer. Okay, so the easiest way to approach this is isomers typically have isomers have the same molecular formula, but they have a different structural formula. So if they ever have a different number of atoms, you immediately know it is not an isomer. So the first thing you typically want to do is count the number of carbons. And that's, I think, what they want you to look for. This has 1, 2, 3, 4 carbons. This one has 1, 2, 3, 4, 5 carbons. So 4 carbons versus 5 carbons, obviously they're not the same number of carbons, so that one's out. Moving on to number 2. Well, option 2. 2-methyl-butan-2-ol is an isomer of hexanthriol. Okay. Isomer of hexanthriol, so hexanthriol will look something like, let's see, 1, 2, 3, 4, 5, that's 6 carbons overall, and then 1, 2, 3, so OH right here. And again, option B. Okay, that's what hexanthriol looks like. 2-methylbutan-2-ol. Okay, so again, look at that butane. So 1, 2, 3, that's for butane, 4 carbons. 2, so right here, OH, for the butan-2-ol, and then 2-methyl, which is like that. Again, taking a look at the number of carbons, you have 1, 2, 3, 4, 5, 6 carbons here. 1, 2, 3, 4, 5 carbons here. So that's not going to be right either. Okay, so we're done with option B as well. Option C. 3-methylbutan-2-alone is an isomer of pentanal. Okay, so that Al right there is for an aldehyde. Pentanal looks like this: 1, 2, 3, 4, and then carbonyl, like that. Oh, by the way, if you're ever noticing, whenever you have that penta or whatever, just draw the number of lines minus 1. So in this case, notice how I drew 4 lines just like that. It really makes drawing things a lot less of a hassle. But yeah, just a quick tip for speed. 3-methylbutan-2-alone. Okay, again, butane is 1, 2, 3 because it's 4 minus 1, 3 lines. And then 2-one, okay, so 2-one would be O right there, so that's a ketone, and then 3-methyl, so that would just be right there. So 3-methylbutan-2-alone is an isomer of pentanal. Okay, counting the number of carbons: 1, 2, 3, 4, 5, so 5 carbons. 1, 2, 3, 4, 5. Ooh, 5 carbons. Okay, okay. We also have 1 oxygen each. And now let's count the number of hydrogens. Okay, so this one's 3, 2, 2, 2, 0, 1. Make sure you count that one, by the way. So let's see. 3, 4, 5, 6, 7, 8, 9, 9, 10. So 10 hydrogens. Now this one, 3, 0, 1, 3, 3. Okay, 3, still 3, 4, 5, 6, 7, 8, 9, 10. 10 hydrogens. What do you know? That is indeed an isomer. Okay. But just in case, let's test that last one. Answer choice D. Okay, 3,3-dimethylbutan-2-alone is an isomer of pentan-3-one. Okay, so pentan-3-one looks like this. So 1, 2, 3, 4, because it's pentan, and then 3-one. Okay, like that. So that is pentan-3-one. 3,3-dimethylbutan-2-alone. Okay, so butan, so 1, 2, 3, 1, 2, 3. 2-one, so like that. And then 3, 3, so just right here. 3, 3-dimethyl. And if we count them up again, see, 1, 2, 3, 4, 5, 5 carbons. 1, 2, 3, 4, 5, 6 carbons. So again, this one can't be either because the number of carbons differ. So answer choice C should be correct. All right. That is it for this video. We'll go on, let's see. Next video, we'll go from 22 to 30. Okay, so a bit less than normal, but hey, what do you know? We're just going with the number of pages. So yeah, hopefully you guys enjoyed. Hopefully you learned something new today. Yeah, that was it from me. I am Yushin, Yo-Yo, whatever you want to call me. You guys have a good day. See you guys later. And I guess see you next time.